Yeah. All right, we should be on. So, as I told you, what I wanted to go over today was our bingo, and then just a recap of Williamson. And then we go to Restall. So before going to the Restall thing, I have to give you a fair warning. We're going to be using a system which is called the sequent calculus. And I am going to give a very, very brief introduction to it. And basically what I need you to know is how the quantifiers work. But that is about it. And I'm going to try to be very intuitive with how this works. So I'm not going to be very precise. I just want you to know how this is supposed to work so that we can work with this. And if you are interested in this system and you want to investigate it further, then that's okay. Then you should definitely go. And then the other thing that we're going to do is to talk about this idea of free logic, which appears in the bingo. We have talked about this, but we have not really discussed it in length. So today's the day. So that means that this is going to occupy us at least like 2/3 of the class, and then the system itself is going to be 1/3. It's going to be so easy to explain once we have the sequent and hypersequent calculus and the free logic, then the system should just go in a breeze. Now, if you want to do the presentation of this, there's a lot of that I'm skipping here over because I am just interested when it comes to Restall. I'm just interested in how he makes Barkan and Converse Barkan fail. And we're going to see an argument for this, not from possible world semantics, but using other tools, namely the sequent and the distant cousin, the hypersequent calculus. So Timon took proof theory, and he's familiar with the sequent calculus. Jan, what do you know more or less about the sequent calculus? Jasper? All right, and here, let me see. Are you familiar with the sequent calculus more or less? So Mateo, Wojciech, Ludovico and Mateo. Okay, good. So if I'm going slow, sorry guys, but I think it's important that we all understand how this works. So normally, so let's talk about the sequent calculus. So normally when we have studied this, we have taken one approach to syntax. And this approach to syntax was that of axiomatic systems. And with axiomatic systems, I mean the Hilbert style calculus. What is this Hilbert style calculus? I show you a bunch of rules that have this form, and then there is a connective here, and then I told you, and there is modus ponens. This is, of course, a very, very important tool in the development of logic and in the development of mathematical logic, especially. And it's super powerful to study and to simplify systems, but it's not I think, the best way to study things if we want to know about how the operators behave. So if you have ever worked or have you had to have homework when they ask you to prove things in the axiomatic systems, it is very hard to work with these. And some people prefer to work with other systems, but the idea is that we change the fundamental unit of proof from a combination of formulas and modus ponens to that of the idea of sequence. So sequence are going to be a formal expression of this form. So we're going to have the same symbol to designate a set of formulas, and then we're going to have two sets of formulas on each side. How are we going to call this one? So this one is going to be called the antecedent and then this one is going to be called the succedent. So there is a problem in how we represent this because this doesn't mean the same as this, and that's why if you read Restall's paper, he's going to represent this sequent arrow as this kind of weird arrow here, a little bit more curved. So this means derivability in an axiomatic system, and this here means that if everything in gamma is true, then at least something in delta is also true. So there's a way to formalize this, and it is basically intuition is that if the conjunction is of the formulas in the antecedent is true, then the disjunction of formulas in the succedent are true. And there is an even more intuitive way to understand this, that it is with the resources that you have on the left are enough to prove the things on the right. So this means that if you have a set of formulas, gamma, and you can show that they take you to delta, then you can apply rules to this sequence to transform the sequence and say, for instance, that this is also true. What does this mean? It means that you have added things, but previously we said that we had enough resources to derive this. So if we add more things, that doesn't change what we can derive. Are we clear so far in how sequence works? So especially talking to you two guys. So if you're at all not comfortable with this, let me know. So the idea of this is that normally we have a bunch of why do we have so we have much more rules. How many rules do we have in the axiomatic system? One. You can make this thing called the derived rules, but you have mainly one rule, which is modus ponens. Here we're going to have a plethora of rules because what we're interested in is to make precise how the connectives work instead of just like being as tight as possible with our system. So normally we have structural rules and we have rules for the connectives. So we're not going to talk about all of them, but I just show you one. This is called left weakening, which means that we have applied weakening, but we did so on the left. There's another rule called right weakening, when you do the same thing, but on the right. So this idea of, it's very important that you understand what is the difference between doing this, sorry, this came out very wrong. And doing this. So both things are good. This is left weakening and this is right weakening. But here it basically said that we're adding resources. And remember that interpretation of this is that this is a conjunction of formulas, while here is a disjunction of formulas. So this means that you have, if this or this, and this means that you have this and this. That being said, there is another important rule for what we're going to do, which is the only rule that lets you like make formulas disappear, so to say. It is similar to modus ponens. It is similar to, let's say, transitivity, but it is called the cut. And the cut rule is going to work like this, and is the first rule that we're going to see that has two sequence, that it works with two sequence. So suppose we have a set of formulas, and from these formulas you can derive A, and from A you can derive another set of formulas. This is our theta, by the way. So this means that if you have this, and if you have it here, this means that you can make it disappear, so to say. For the people well versed in this, I'm using the additive version of the rule because I'm using different sets of sequence in both. So the idea of this, if you interpret it, is that if you have enough resources to derive A, and A is a research to derive theta, then we have the resources to derive the same stuff without A. There's an easier way of seeing this if you're interested in it, and let's say this is the other version of the rule, but I guess you're familiar with this already. So, well, these are called the structural rules. We're not going to talk about how they work, but the promise that that people do when they work with these rules is that when we use the rules for the connectives, what we are doing is somehow establishing the meaning of these connectives. Instead of simply explaining an axiom of what is the minimal logical behavior that this connective has, we're doing something about the meaning of this. So, for example, the rules for the conditional, the material conditional, would be as follows. So if you have a sequence A, a sequence that derives A, and you have another sequence in which B can derive stuff, then you have a sequence in which A then B can derive the same stuff. This is known as conditional on the left. And we can also talk about the introduction of the conditional on the right. So this rule will say that if you have enough resources to derive B from A, then you have enough resources to derive A from B. Does somebody know the other name of this rule in the axiomatic approach?
Deduction theorem?
Yes. Why? Do you want to say something about it?
It like visually, if you have deduction theorem states that if you from gamma and A can derive B, then you can from gamma alone derive A implies B.
Yes.
So like visually, like this just does the same thing.
Mm-hmm.
Is all I have to say.
Yeah, no, great. That's it. Basically there is a very, very tight connection between the conditional and the deduction arrow. So here we call it the sequence arrow, and then this is going to tell you that all these systems are connected. But well, questions on the sequence calculus? Because now we're going to spice things a bit. Because I'm sure that maybe none of you have. Maybe Mateo knows about what I'm going to talk about right now. But once you have a graph of the sequence calculus, the idea is that you can do a lot of logic with this. In fact, you can do some modal logic with this, but you cannot do all modal logic with this. You can also do quantified logic with this. You can do first order, second order logic, but you crucially need more stuff to do quantified modal logic because of the modal part is not, so the sequence are not enough. So we're going to study the hypersequence calculus. And this is when it becomes interesting. Because a hypersequence is a finite multiset of ordinary sequence. So to write a hypersequence, this is my notation for this, so this other ones, you're going to simply say that here's a sequence, and then you're going to use this bar to say that you have another sequence, and then, well, you can have even more of those. If we previously said that this means that all the formulas in the antecedent are true, then some formula in the subsedent is true. What could all this whole mess mean? Or I'll give you the answer. So it's at this junction of the sequence that we have. So we will have the conjunction of this implies that this junction, this one, and then I'm going to skip the second one, but it's basically does it make sense now that you see? So of course, when I tell you this, and when I tell you something like what we had here, this is a way to interpret it in terms of truth. But here we just have the sense of following from rules. We don't have only the sense of proof. So this sounds like truth conditions, and is a way to understand them. This is not exactly what this is saying because we don't have a notion of truth in here. Well, yeah, let's say that. But now, what I needed to keep in mind is that when we go into modal logic and we use this, each component is going to represent what we're going to call a zone. So every subsequence we're going to call it a zone. So what are zones and why are they not possible worlds? It's a difficult question, two difficult questions, but if you want to call them possible worlds, do it. I mean, I don't care. But possible world semantics, so possible world are related to possible world semantics, and here we're not giving, again, we're giving us semantics. We're giving a way to do proofs. So if we interpret this as the zones, so if we read this on the line of this, basically is saying there is a logical entailment, at least in one of the zones. at least one of the zones, there has to be this thing that from the resources, you can derive everything on the right. Now, the rules are going to change a little bit because we're going to have rules that are going to be not only structural and for the connectives, but we're going to have internal and external. The internal rules are the ones that apply. So internal rules are the ones that apply in a sequence, in a zone. So we can govern the logical vocabulary in that zone. But then there are external rules in which we can govern the behavior of the whole hypersequence. So two of the most important rules that we're going to see are the rules that are for the modal logic, and these rules imply, we need this idea of external rules. So I'm going to give you two examples of external rules and how do they relate to the other system that we have before. So in sequence calculus, we have this very interesting rule, which is called the contraction rule. And it says that if you can derive something from two copies of the same thing, then you can derive it with only one copy. Right? Now we're going to have something similar. So in the hypersequence calculus, every sequence is going to have this rule, but the whole hypersequence is going to have something very interesting, which is called external contraction. So we're going to say that I will explain what the H means later. For the time being, ignore the H. Sorry, I should have introduced it earlier. But the A, what we're saying that it is if you can derive if this or this, and they are the same set. So notice that here, gamma, the gammas and the deltas coincide, right? So if you can derive it from this one or from this one and they are the same, well, you can derive it just from one. So the idea is that this works is as if you had something like from P or P, you can derive Q, so you can derive it from P. Is this good? Do we have questions? Is it okay with you? All right. So the difficult, now what is this H that I'm putting here is a variable for the hypersequence. So this could be possibly empty, but it could be other sequence. So the idea is that for any hypersequence that behave like this, you have to still keep it. This is just as in the idea of the sequence calculus when we have these things. So these things could be possibly empty, sometimes for some rules, but the idea is that you keep them as variables of sets of formulas, and here you're using this as a variable for sequence in a modal sequence. All right. So I'm going to spoil a little bit what we're going to do with the modal rules so that you have an intuition of what we're going to have. So the first thing is that in modal, this is redundant, let's just call it S5. So in S5, what we're going to have is the idea of modal transfer. So since in S5, the accessibility relation is universal, so if there are two worlds, for any number of worlds, if they're connected in any way, they can see each other. So if they can look at it, they can also symmetric, it's also transitive, it's everything else. So what this is going to tell us is that the idea is that if A is true, this is the intuition, then so if box A is true, then A is true in any possible world, right? And the intuition for the hypersequent calculus is that if you have A in one sequence, you should be able to move it. Let's say that you should be able to move it to any other one. So this is not the rule itself. This is badly written, but this is just so you grasp the intuition. The idea is that if you have a box, then you can move the content of the box across zones. So this is what is sorry. It was only not badly written, it was terribly written. So the idea of this is that if something is going to hold in a zone, then you can move it across. And this is important because for the quantifiers, it's going to work like this, but for the modality, it's going to work like this, but for the quantifiers, it's not going to work like this. I see your troubled face.
Well, it seems like we could already add just by internal right weakening.
Yes, but the idea of this is that if you internal right weakening, yes, but give me a second because the rule has a complication that the actual rule, this is the intuition, has a complication that tells you actually need some other stuff. Because if you see it, what happened to the zone where the necessity was there?
Okay.
If you applied, so sorry if I'm getting ahead of myself, but the idea of the rule is that this zone disappears. If you put weakening, you still have the baggage of this one. And the idea of these rules is that they work as definitions. So you can go back and forth. If you put it as weakening, then it is weird to say, hey, if I have weakening, and then I have this, hey, is this a suitable definition for the box? Well, no. But you're on the right track, but you're getting a little bit ahead of ourselves. All right. And the other idea that is going to be important is the idea of a modal definition. And the idea of modal definition is that instead of giving you truth conditions for the modal operators, so normally in semantics, what I tell you is, I tell you, hey, this is true. Oh, sorry for the typo here. When is this true? Hey, if it's true in every possible world which is accessible to W, right? But here what I'm going to give you is a definition. So we're going to reject this kind of way of making explicit what the box is giving us, and we're going to give instead a definition. And a definition is going to look something like this. We're going to have a hypersequence here, and we're going to have a double bar to another hypersequence. And then we're going to say that this is a definition. This is not exactly, this is not technically the best way of saying it, but for the purpose of this project, I am forced to do it like this. And the fact is, the only difference between a rule and a definition in the system is the fact that we have the double bar. Do you see the double bar? Oh, see. What does the double bar means? You can go this way. But if you have, so let's do this better. This is basically saying that if you have this one, you can jump to this one. And if you have this one, you can jump to this one. Proofs are always read from top to bottom, but no, sometimes in the proof theory paper, they say, oh yeah, the proof is this proof, but read the other way around. So there's that. All right. How are we doing? Any questions so far? Yeah, Magnus?
Yeah, okay. So it's just I could use a bit of intuition or let's say motivation for doing this construction. Because like usually the way I think about the box, right? If we have a first order logic, it's sort of a bit too big to be ruly. Like modal logic has some very nice properties, and we get those properties by saying instead of saying for anything in the domain, we just restrict it to say anything accessible via some relation.
Yeah.
But here we've weakened the quantifier by saying instead of saying it ranges over the entire domain, it just ranges over a zone. But then we take the box and now it's ranging over all the zones. So it's sort of like the quantifier has been sort of weakened and the box has been strengthened a bunch. And I am just wondering what is like, is this philosophically motivated specifically, or is there some other reason we do it this way?
So that's a great question. And maybe I don't have the best answer for this. So if someone knows it, please tell us. But I think the point of this is to make it in a way in which the modal logic works. So mathematically, you can see it as merely saying, yeah, we just needed a way in which to make S5, and we found this one, and it's actually sound and complete with respect to S5. But the point of this is sound and complete with respect to cryptic semantics, right? We're not changing the semantics, we're changing the syntactic apparatus that we have. The novel and the interesting philosophical thing is that this gives us a view into the meaning of the symbols. So the point is, like you said, like we butchered the. If I get to, if I'm reconstructing the idea well, is that we are restricting in the meta language how the box works, but the point is that we're not. So if you go to in a hyper sequence S5, maybe I'm gonna do this wrong, so please. The idea is that if you have this, and if you have this, no. I put the H at the end, but please bear with me. Then you have this. And the idea of it is that if you, I'm not sure how this, no, sorry, man, I'm going to answer, I'm going to have to answer this question later because I have to look up the rule again, and then maybe I'll answer the philosophical part. Would that be all right?
Perfectly fine.
All right. Yeah, so, yeah, let's go. Okay. That being said, let's take 10 and we'll back at 10 past. Zoom recording. All right. So we had a great discussion here of why I wrote the rule wrong. and I was trying to make it more intuitive, but I didn't. And the point is that here's the rule, in case you're wondering, we're going to see it again. But the rule says that if you have a zone in which something, a derivation goes, and then you have an arbitrary zone in which A is, you can derive A, not sharing. Fuck this thing.
Recording in progress.
We're back. So when I was writing the rule, I did it not the way it was supposed to work. I did something different. And basically, I messed up where the box went. So the rule in the hypersequent calculus basically says that in a zone for which you have some truths, you have some derivation, and then if there is another zone in that hypersequence in which you can derive A arbitrarily, it's A, then you can derive in that hypersequence box A, and you make away with the zone in which A was true. So it's more powerful than just weakening, because in weakening you will have to tell me what happened with the arbitrary zone. But now it's the correct interpretation, because and to see this maybe more clearly, think about it and read it the other way, from up, from down, from bottom to top. And the idea of this is saying that if you can say that something is necessarily, if you can derive necessarily A, then you can derive it A from any zone without any other premises that we need. So sorry, and thank you for pushing me in this thing. And I haven't shown you or mentioned right now so far the rules for the quantifiers, because what I want to say is I want to introduce. Oh no! Wait! Introduce them in the context of this fantastic logical setting, which is called free logic. So, anybody familiar with the free logic here in the room or online? Anyone familiar with free logic? No? Oh, okay, I see. So. That's good. So, free logic, what basically was the interest on deriving it, is to talk about this thing that has appeared in the bingo, which is called empty names. So emptiness, so let's write stuff out because we have a board. So free logic. So the idea of free logic is that in traditional quantified logic, we don't have a way to refer to things that do not exist here, or that are mere fictions, or that are simply, we cannot make a distinction between things that exist and things that don't, because everything in the domain implicitly is already existent, so to say. So how do we make that explicit in a quantified system? You make it so that for every constant C, it is the case that there is some x that x is equal to C. So there is something in the domain which is going to be identical to that. Free logic is going to reject this in order to talk about something like Pegasus, Sherlock Holmes, etc. But in modal logic, we can use it to handle contingent existence. And for that, I'm going to tell you what is the intuition of how we put this first in a simplified system. Then I'm going to tell you how the semantics work. I'm going to show you how it works for the sequence calculus. And then we're going to move to Restall system. So I told you there was a lot of preamble here. So let's go straight. So in classical logic, we have this instance, so this schema, which is called we have called instantiation. Let us, for the purpose of this session, call it classical instantiation. In free logic, this inference is invalid because you can make interpretations in which you have T, but T may name a non-existent thing. So what is the option that we have? So this is not valid in free logic because it can be the case that there is not an x such that x equals to t. So to fix this, we're going to create a new predicate, the existence predicate. So in free logic, the first thing we're going to do is to create a predicate. And more often than not, this is defined as there is an x. So this for t exists if there is an x that is t. So with these tools, we can go and change our schema for instantiation. And then we say that if for all x and t is an existent term, then you can instantiate that to t. See the little change that we did there? Here we had it unrestricted. And here, now we have this condition in mind. We're adding more things. So you cannot just go willy-nilly and say, yeah, for everything this, wait, you can still say it for everything this is the case, but you cannot apply an instantiation. So this is when I hope that the difference between an actualist and a possibilist semantics is starting to become a little bit more clear. And now I'm going to tell you how this works in terms of domains. So when we talk a little bit about this, we understand, sorry, in the quantified modal logic sense, we understand more or less what we're going to do. And the idea is that, so, no, sorry. When we go to the semantics of this, we're going to have a model which is going to have three things. It's going to have a domain and another domain and our interpretation. So what is going to be interesting and different between these two things? This we're going to call the outer domain, which is all the logical existent things. So everything that you can actually like assign a constant in the, all the constants of your language. And then you're going to have the inner domain, which you're going to, if you see the E there, it's because are the things that are existing. So there is this restriction. So D is outer, E is inner, such that, let's put this like this, such that E is contained in D. But then we're going to have this interpretation that it works, as you know, but the idea is that it assigns something to everything in the outer domain. So if you're wondering about the truth conditions of this, so the truth definition, basically in a model, this is true if and only if the interpretation of C belongs to interpretation of P. But we also have this special clause of the existence, and it is if the interpretation of C is in the inner domain. And as I told you, now quantified statements become much more powerful. Because they start meaning different things. So every substitution instance makes it true of the inner domain. No, it is a mistake. All right. In terms of rules,
I'm just confused. Like, it's basically the variable sense range of the outer domain.
Yeah.
And isn't the existence predicate kind of always, or I guess if we just define it like this, it's not that. So.
We're getting there. Don't worry. So, normally, so quantifier rules. Normally, when we're in the sequent calculus, the rules for the quantifiers, so sequent calculus, tells us that if you you know the eigenvariable condition? No, that's right. I'm going to try to explain it simpler. So Y here is a term that does not appear anywhere else. So if you can, and it's an arbitrary, in natural deduction, they call this arbitrary terms, arbitrary constants, or how you set up your language. If you have this, then from an arbitrary that is not bound in the lower sequence, then you can say for all of them, right? But in the free sequence calculus, we're going to have instead this version of it, which says there is a condition upon which you have to say that it exists. I'm gonna let you time to dissect this formula to understand it. So what is this trying to do? This is trying to reclaim this scheme that I told you about. So this and the following rule. So we have this, and in the sequent calculus, we have another rule that says this basically tells you how to introduce the quantifier on the left. But here we're going to add another thing. So if you have A of t, then gamma, then delta, then what you're going to end up with, if you want to quantify, is that you have that for all of them, yes, but you have to make a note and say that this exists. So unlike in classical logic, simply having for all x, a of x, is insufficient to conclude that there is an arbitrary term t. So now the sequence always has to have this existence predicate somewhere. And the existential rules, I'm going to go very quickly over them. So basically, in the sequent calculus, you may say that from this, you may derive this is the introduction of the existential quantifier. Says if you have something, then there is if t has a, then there is something that has a. And on the other hand, it says that if there is a term that has a, then in the free version, so this is in the classical thing, and in the free version, you're going to do the same. You're going to have the formulas, the existence things somewhere. So in the case of the right rules, what you're going to have is that if you can derive this from this, then under the condition that t exists, then there is something that has this. So t is being like the witness of existence with this. We don't only need something in the domain, we need an actual existing thing in it. And then all right. This captures free logic. And then if you have questions about free logic, any questions right now?
The truth definition, I think you wrote it as using the outer domain, but should I use the inner domain?
Yeah, I think I corrected it. And now I'm not sure, but I think it is like this. Yeah.
That's also what the notes say.
Yeah. Yes, I got confused with what I was writing, thinking, and the notes. So thank you for this. All right. So why is free logic useful for this? So for quantified modal logic, because there are various versions of this. So there's negative free logic, and all this is going to questions like how we can do things about this and how this helps. And also there's negative free logic. So in the families of free logic, there is a negative, a positive, and a neutral version. So negative free logic says that any atomic formula containing an empty term is false. Positive free logic are going to say that some atomic formulas containing empty names are true. So some atomic formulas containing empty terms are true. And what is the difference? So if we want to say, for instance, like Pegasus is a horse, I want to say no, it's a mythological creature. It is not a horse, and everything in the nothing in the world is going to satisfy Pegasus, empty name. So this should be false. Anything you say about Pegasus is false. But sometimes we want to say that despite this thing not existing, there are some properties that it has. For instance, it's a mythological creature. So we want to say that, hey, yeah, Pegasus does not exist. I'm going to grant that. But there's something we can still say about this thing. And what are we referring to? Well, that's another philosophical discussion, maybe the collective idea that we have of Pegasus or how it is represented in a certain tale, certain book. And neutral free logic is that formulas that that contain empty terms lack of truth value. So this should ring a little bit close to home for those who took MRM, and this is because this is what Hamut sometimes tries to push a little bit when he makes this standard variant domain semantics and modified variant domain semantics with this partial valuation. Because this basically says everything that you say about Pegasus is going to be no, you cannot assign a truth value to this. And then with the neutral logic, you can also split hairs and say, okay, some of them are backwards, or they have a truth value gap, and some of them don't. We're not going to enter into that discussion. All good about this, so we can finally go to the contingentist system. All right, so Restall. So I'm going to maybe take a little bit, go a little bit over 4. So if you need to go or anything, it's okay. But so that you know, I mean, there's the recording and everything. But I'm going to be as quick as clear as possible. But if you need to leave at any point, don't worry. So as I told you, the idea of Williamson is that he wants to reject traditional model theory. He said that model theory is neutral and it is not enough to talk about actual or like the metaphysical modality that we have in the world. He rejects that because you can build models where the bar can and a complex bar can fail. And Restall is going to say something that is even more extreme than that. So whereas Williamson rejects traditional model theory but still stays within some modified version of model theory, Restall is going to say, no, we should reject possible world semantics altogether as an informative way of making meaning of the quantifiers and modalities. What we need is what I told you about, but we use definitions of these things that are informative on how we use them in inferences. This is very broadly characterized as inferentialism. So the introduction and elimination rules determine the meaning of the logical symbols. This is a way of doing inferentialism. So this is connected with something that it is very hot today, which is proof-theoretic semantics. But proof-theoretic semantics is a version of inferentialism in which there's like two ways of explaining this. Basically, is the notion of proof. It is as like logically legitimate as the notion of truth. So truth in a model, it is the same as doing. There's a proof for this. In fact, there's people that say we should just focus more on proofs than on models. And then there is people that take another step, take another way, and a little bit more mathematical, and do something called base extension semantics, in which basically they try to create models from logical rules. It's super interesting, and do check it out if you're interested. But Restall is a little bit more in the first camp, the idea that proofs are as good as models. In fact, it's going to say in the case of quantifiers and modalities, they are better. And then I'm going to read this. Where is it? Here. This small passage from Restall when he tackles the idea of using possible world semantics. So I quote, any insight gained from employing models for modal logic is partial, since if we wish to use possible world models as the representations of how things really can be, modally speaking, we must rely either on identification between the indices of a possible world model and some antecedently given class of possible worlds, or we must give some other account of how and why it is that these models accurately represent modal truth. Merely stating that a given model represents modal reality does not make it so. So here, my interpretation of this is that he is attacking directly this position of Williamson that we can represent how metaphysical necessity in possible world semantics. Is going to reject this altogether because he says you are presupposing that possible world semantics is a correct approach, and that you can map every index in a possible world model with some ways the things can be. And this is wrong from his perspective because this tells us nothing. So first, he's like, the problem with this is, of course, that you are supposing that somehow this model is an adequate model, and then your conclusion is, oh, I found a model which is adequate with respect to metaphysical universality. Well, maybe that's suspicious. So what about we understand how the quantifiers work, and then we go around and the modalities work, and then we see if this validates any philosophical thesis. So as I told you, we're going to be in the realm of the hypersequent calculus, and we have zones. So remember that we had this sequence within a hypersequence, and this represents these so-called zones. These are not possible worlds. We are not doing semantics again, but they are just so similar to possible worlds. But I mean, it's a feature in a block, I guess. So, and we use H as a variable ranging over hypersequence. So the definition that we're going to propose for the modal rules is the following. So we already saw how diamond works. I'm going to write the rule again. I'm going to stop writing the parentheses there in the notes, but I just realized they are taking me a lot of time to write, and maybe they are not that clear. Then this is what we saw previously, but now we're going to write the other line here, and we're going to say that this is the definition of this. And if we go to the diamond, what we're going to have is that so this basically says if you can use A as a resource in an arbitrary derivation, then it is possible in any cell. I wish I had a more intuitive reading of this. I have turned it upside down to try to understand what is this telling us. And I don't have a good explanation for it. If you have one, you're more than welcome to try to explain it to us. But I don't. Sorry. So, does anybody wants to give it a go?
I'm just kind of like, does the dot represent the empty set here?
Yeah, I'm not sure. I think it does, but
I don't think I've ever seen a sequence with an empty.
Yeah, let me check.
That.
Yeah, I took this, but maybe he was not careful enough. Where this, God, where are you? Scalar quantifiers, possible possibilia. Always. If you are just arriving, I'm looking for the rules. Yeah. So I have them here. Yeah, so it's empty. That's why I put the dot because I. So. Okay. Yeah, I'm not sharing. So. Yeah. So. Restall says the idea is straightforward. To deny necessary A. Oh, I'm not projecting this. I'm not sharing anything at this point, actually. What do I do? Do I have time for this? So I'm going to show you the rule. This is page 13. So yeah, they're in. And I can wrap my head around the first, pretty easily. But this one I still, so the best I can do is tell you what I told you, like if in a zone you can use this as a resource, then possibly in any of the other zones you can use possible as a resource. And then he has this explanation that I'm not really sure I understand. The idea is straightforward. To deny a box A in a zone of discourse is to be out of bounds given other commitments to the sequence gamma delta and the hypersequence. If denying A in some zone is out of bounds relative to those commitments. To assert possibly A in a zone of discourse is coherent. To assert A is possible A in a zone of discourse is coherent if and only if asserting it in some zone is coherent. Possibility and trade on this shift of zones. So this is S5 supposedly, and one of the things that I really like about talking with inferentialists is that maybe they fix the meaning of stuff, but it's the meaning that is not comprehended by humans, because some of these rules I just go with the flow with them, actually, to be completely honest. So if you take Restall system, please think about what the possibility rule is telling. I guess this is not a satisfying answer. Sorry. We have to keep moving. So yeah. So what happens with respect to quantification? As I told you, all the rules that we have for the connectives and the quantifiers you can use in every zone, but you have to respect the zone where it happens. The difference that we're going to have is that modalities can go across zones, but quantifiers cannot go across zones. This is what Restall calls there's no migration in the quantifier. And then he has discussion of why the free interpretation is adequate for this, but basically the rules are going to be the same, but relative to zones. I'm just going to write these two. But I guess you can infer the other ones. And what we have here is, again, not a mere rule, but we have a definition. That line came way wrong. So this is the definition of the universal quantifier, and this is the definition of the existential quantifier. So this basically tells us, and what we can see is exactly that we have systems where domains can vary. So an object may satisfy. The idea is that you think of zones in which this may be a thing, but at the same time, this is the case. This is a valid hypersequence, for instance. So claiming that something is true in a zone doesn't commit us to making it true in all zones. this is a intuitive reading of what I'm trying to do. This is not a rule or anything. Yeah, now I've become very wary of writing pseudo hypersequence. What just happened? All right, so we're going to try to see how we have failure of BF and CBF. But if you have to leave, it's all right. There. So the point is that the Barkan formula, this time I'm going to write it properly, says this, right? So it says if everything actual is necessarily P, for instance, then necessarily everything is P. So in the paper by Restall, there is the nice proof in the hypersequence, but since I'm not expecting everybody to be familiar with the sequence and the hypersequence, we're going to reconstruct this in English rather than see the proof in the hypersequence calculus. And if you're interested, go to the paper. It's very good. So first, we're going to assume for all x in zone 1, right? So if we use the definition of the quantifier for any A existing in zone 1, we have box PA. So we assume this, we instantiated what is exactly what that we're instantiating. So remember that we have this scheme that says for all x, px, and arbitrary A, we are going to have necessarily PA. We're good with this? So this is just over the existing things in zone 1. So by the definition of necessity for any A, PA is going for for any A, then in zone 2, PA. Again, this is the rule that we had that said that if you have in this zone, then you have it's the rule again. I'm now scared I'm going to mess it up. Then this is right. This is what the rule says. Let's make it a little bit more contentful so that we are happy with it. Good. So our goal should be to prove that necessarily for all x, px in zone 1. But this requires to prove, so we need to prove for all x px in zone 2, right? If we prove that this is in any arbitrary zone, then we can import it to zone 1. But to prove for all x p of x in zone 2, we need to pick a fresh b, assume that it exists, and only then answer and prove that PP. And this is where the problem comes. The problem is that we know PA is true from what from zone 1 for objects from zone 1. But this thing that we said B is, let's say, native to zone 2. And we don't know if B is in zone 1. So if B does not exist in zone 1, so if B does not exist in zone 1, the premise for all x, which was from zone 1, tells us nothing about B. So even if we have this, since we created B in zone 2, we have no way of saying what is it with B in zone 1. So this is where the magic of the proof comes alive. It says, like, I'm giving you the most basic quantifier rules, because Williamson said, hey, my system is the most basic one. But here's the catch. If I give you the most basic quantifier rules, you can't derive that. So I need to open something here very quickly. That Restall says, like, how we could recover things. So to actually work, we need migrations for terms. So migration rules are rules that make things in the same hypersequence move from one sequence to another one. And for terms, this would take the following thing, the following shape. So I have a term here, and I don't have it here, but I can move it to the other zone. So this would mean that I have my A or my B in zone, I have B in zone 2, the term we're talking about, and I can move it into zone 1. But that would be assuming, in our weird way of speaking of this, constant domain, right? But we already agreed that we are having the simplest quantifiers that we can have for the system. So this is adding more to this, and it basically tells us nothing about the quantifiers. I mean, you can maybe add in and have a system that is just sound and complete, whatever. But what is the motivation for doing this? That's kind of the problem. And Restall said like, hey, you were talking about simplicity. That's it. Well, here's simplicity. All right. There's also the rule, the failure of the converse, and the converse says the following. So I'm going to go a little bit faster around this one, and this is in zone 1. This means that in any zone K, and I run out of power on my Apple Pencil, so I'm going to show you how it works. Today was not a great day for online sessions. Let me tell you that. Is it still? Yeah. So this means that in any zone K, everything existing in K is P, right? So we now need to prove in zone 1 that for all x, necessarily P of x. To prove this, take any arbitrary witness A and assume that it exists in zone 1 and try to prove necessarily PA. To prove it, we must show that PA holds in arbitrary zone 2 by the definition of how the box works. Remember that if you want to introduce it, you need to show that it holds in an arbitrary zone. But the gap is that to conclude PA in zone 2, we would need to show that A exists in zone 2, but we only assume that it exists in zone 1. And since identity does not imply necessary existence, so we reject that in general, so necessarily we're going to reject necessary existence. We cannot transfer the object A into the zone 2. So the derivation is blocked again. I hope that despite all the trouble we had for this session, you were able to take something out of it. And I'm going to leave it there unless there are any questions. Oh, I was not. So I'm really sorry with the people online because Zoom kicked me out from the tablet at some point. So, okay, but the proof is in the notes, or the argument is in the notes, but okay. So I see that there are no more questions. I'll try to improve things for the people online next time, but I'm going to stop the recording right there.